Hello everyone. In this lecture, we will define orientation of a surface and also we will define normal unit vector field defined on a surface. Let us begin. Let us take a regular surface S in R3. And let us take a point P belonging to this S. So this is my surface S, and suppose this is my point P. And now you take the tangent space to the surface at the point P. This is my tangent space at the point P. Okay, and now suppose this P, it is contained in two regular surface patches. Suppose this is my this is sigma of u. So sigma, it is a map from this u to this surface. Corresponding to this sigma, I'll get a basis of this tangent space at the point P. So sigma u and sigma b, it forms a basis of the tangent space at the point P. And now if I change the surface patch, so suppose the next surface patch is u tilde sigma tilde. So I'll get another basis for this tangent space. Okay. All right, let me write down. Let u sigma and u tilde sigma tilde be two surface patches at the point P. Now see sigma u, sigma b, so it forms a basis for the tangent space of S at the point P. And also sigma tilde u tilde, so this also forms a basis for the tangent space. Okay. Now, so how this two bases are related? So they are related by the Jacobian matrix. Okay. So sigma tilde u tilde. So this is equal to sigma u multiplied by del u tilde plus sigma b del b del u tilde, and sigma tilde b tilde is equal to sigma u del b tilde plus sigma b del b tilde. Okay. So if I take the Jacobian matrix, so Jacobian matrix is given by the following, which is equal to del u, del u tilde, del u, del b tilde, del b, del u tilde, del b, del b tilde. So this is my Jacobian matrix, and uh, the determinant of this Jacobian matrix is given by this del ub del u tilde b tilde. So this is equal to the determinant of this Jacobian matrix. Okay. So now let me define what do you mean by orientation class. So how do you define this orientation class? So we have two bases for the tangent space TPS, and they belong to the same orientation class. So sigma u, sigma b, and sigma tilde u tilde, sigma tilde b tilde belong to same orientation class if the determinant of the Jacobian matrix is greater than 0. If this is greater than 0. Okay. Now what is my definition of orientable surface? A regular surface S is called to be orientable if it is possible to cover S with a family of surface patches in such a way that if a point P belonging to S belongs to uh, two open sets sigma u and sigma tilde u tilde for two surface patches u sigma and u tilde sigma tilde. So then del ub del u tilde v tilde. So this is the determinant of the Jacobian matrix. So this is greater than 0. Okay, so whenever you have overlap uh, between the surface patches at the point of the intersection, so this determinant of the Jacobian matrix it should be greater than 0. So if you have this thing, so then we call that surface S to be orientable. The choice of such a family is called an orientation of S. If such a choice is not possible, then the surface S is said to be non-orientable. Okay. So we'll come to examples and non-examples in a moment. Uh, Before that, let me define what you mean by normal vector field on a surface. By a differentiable normal vector field, normal unit maybe I'll just change the language. So by a differentiable unit normal vector field on an open set U of a regular surface S in R3, we shall mean a differentiable map N from U to R3, which associates to each Q belonging to U a unit normal vector NQ to NQ. So this is a vector in R3 to S at Q. Okay. So what do you mean by normal vector here? So this is my surface S, and suppose this is my open set U, and take any point Q in this open set and take the tangent plane. So take the tangent plane and take the vector which is orthogonal to this tangent plane, and you take that vector to be also unit normal. So this NQ, it is uh, orthogonal to this tangent plane. Okay. So now first let me prove this proposition which says the following. A regular, smooth surface S is orientable if and only if there exists a differentiable field of unit normal vectors n from S to R3. Okay. All right. So how to show this thing? Proof. First, let us assume this S to be orientable. Okay. And I want to define a unit normal vector field on this orientable surface. So S orientable, so then I can have a family of surface patches, okay, such that if a point lies in two surface patches, okay, so then the determinant of the Jacobian matrix corresponding to the change of the coordinates, it will be positive. Let so this script f be a collection of connected surface patches on S such that if P belongs to sigma u intersection sigma tilde u tilde for two surface patches u sigma and u tilde sigma tilde, then so this matrix, sorry, this determinant of the Jacobian matrix will be greater than 0. Okay. So now once we have this thing, so now let us define this this unit normal vector on the surface patches. Okay, so let me draw this picture. So this is my surface S and this is my point P. And let us take the tangent plane here. Okay, and let us take this basis sigma u, sigma p. Okay, and Now let us define. So define n sigma p to be equal to this vector product of sigma u and sigma b. So this vector product, it will be normal to the tangent plane or orthogonal to the tangent plane. And to make it unit normal vector, so what you do, you normalize. So divide it by norm of sigma u vector product with sigma b. Okay. So this n sigma p is orthogonal to all tangent vectors at P. Okay. Now if this P, it belongs to another surface patch, so if P belongs to sigma tilde u tilde, so then for this u tilde sigma tilde, we will get a unit normal vector n sigma tilde of P. Okay. And so now observe this thing. So if I take sigma tilde u tilde vector product with sigma tilde v tilde, so this is equal to del ub del u tilde v tilde multiplied by this vector product sigma u with sigma b. Okay, so check this thing. Okay, so therefore, so this n sigma tilde p, which is nothing but sigma tilde u tilde vector product with this divided by this norm. This will be equal to del ub del u tilde v tilde divided by mod of again del ub del u tilde v tilde times sigma u vector product with sigma b divided by norm of sigma u vector product with sigma b. Okay, so therefore, so this is equal to lambda ub times n sigma p. Yeah, so where this lambda ub is equal to sigma ub divided by sigma u tilde v tilde, this whole divided by mod of the sigma ub sigma u tilde v tilde. Okay, so now this del ub del u tilde v tilde, it is greater than 0 because we have taken this surface S to be orientable. So this will imply that this lambda ub is equal to 1. Okay, so therefore this n sigma tilde p is equal to n sigma p. So therefore, if I take a point which belongs to two surface patches, so we'll get a well-defined unit normal vector corresponding to two surface patches. So now define NP to be equal to N sigma P. So this definition of N is well defined. So S smooth, it implies that partial derivatives of sigma exist up to desired order. Okay, so this implies that N is differentiable. Okay, and N is also normal to the surface. Okay, and now conversely, suppose you have a unit normal vector field. So N be a differentiable unit normal vector field. Okay. Okay. So we want to prove that the surface S is orientable. Okay. So let us take a point P belongs to S. So let P belongs to S, and U sigma be a surface patch such that U is connected and P it belongs to sigma U. So sigma it is a continuous map, U is connected, sigma U will be also connected. So this will imply that sigma U is also connected. Okay. So corresponding to this sigma, again we have a normal vector field defined on this U. So N sigma, so this is defined as sigma U times sigma B divided by norm of this vector product sigma U sigma B. So all these things evaluated at the point Q. So here also all this sigma U sigma B, see these are evaluated at the point P. Okay. So this N sigma U to R3 is a, so sigma U to R3 is a normal vector field defined on sigma U. Okay. And also we have this N, it is a normal vector field, unit normal vector field defined on the whole surface. And this n sigma, it is defined on some open set coming from this surface patch. Okay, so now let me take this function. So let fp is equal to the dot product of this np with n sigma p. Okay. So now note that, so this the value of fp, it can be either plus 1 or minus 1. fp equal to plus 1 or minus 1. So why this is true? Suppose this is my surface S, this is my point P, and I have taken this tangent plane, and suppose this is my NP. So this NP, it is a unit normal vector, okay, to the surface S at the point P. And this N sigma P, it will lie in this line, okay. So either this N sigma P, either it will be equal to NP or it will be minus NP, okay. So n sigma p, either it is equal to np or it is equal to minus np. So because of that, fp, either it will be plus 1 or minus 1. So this p, it is varying in this u, sigma u. Sigma u connected. So this will imply, uh, so n restricted to u is, or let me write, so f restricted to sigma u is either plus 1 or it is minus 1. Okay, so this will imply that n sigma is either equal to n or n sigma is equal to minus n on sigma u. Okay, so now let us take, so let us assume, so n sigma, let us take this n sigma is equal to n. Okay. Now, this is my surface S, this is my point P, and this is my uh, sigma u. So this P, it can contain in another surface patch. Again, this sigma tilde u tilde, I'll take it to be connected. So suppose P belongs to sigma tilde u tilde for any other surface patch with u tilde connected. Okay. So now if this n sigma tilde p is equal to minus np, so then what we'll do? So then interchange u tilde and v tilde for sigma tilde u tilde v tilde. Okay, so if we interchange, so then what we'll get? and n sigma tilde p. So this will be equal to by definition sigma u tilde vector product with sigma tilde v tilde divided by norm of this, and this will be equal to, so here this will be sigma tilde v tilde vector product with sigma tilde u tilde divided by the norm of this, and this will be equal to n of p. Okay, so thus we can cover S with connected surface patches such that if P belongs to sigma u intersection sigma tilde u tilde, then so this Jacobian of the determinant of the Jacobian matrix, it will be greater than 0. Okay, so this proves that S is orientable. Okay, so now using this, you can show many surfaces are orientable and some surfaces are also non-orientable. So let us begin with an example of orientable surface. Sphere, torus, are orientable surfaces. Okay. In general, if I take a differential function, so let f be a smooth function with so let f be a smooth function defined from R3 to R, and a belonging to R be a regular value of f. So then what we know that, so the surface xyz in R3 such that fxyz is equal to a is a regular surface. Okay, and now if I take any point x, y, z in this surface and take the grad, so grad of f at the point x, y, z, which is this vector, so the partial derivative of f with respect to x at the point x, y, z, take the partial derivative of f with respect to y at the point x, y, z, take the partial derivative of f with respect to z at the point x, y, z. So this grad is normal to S at the point xyz. Okay, and let us take nxyz to be equal to this grad of this fxyz divided by the norm of this grad. Okay, uh, so here note that, so this grad of f at any point xyz is not equal to 0, as a is a regular value. Okay, so this n defined on S, so it is a unit normal vector field, is a unit normal vector field, and F smooth implies that n is differentiable. Okay, so from here, so what you can show that the sphere, unit sphere, it is an orientable surface. All right, so now let me give you an example, which is a non-orientable surface. Mobius band. So how do you define Mobius band? So if I take a square, unit square, like this, and if I take this point xt, or let me be precise. So this coordinate of this corner is 0, 0. This is 1, comma 0, and this is 1, comma 1, and this is 0, comma 1. Let us take this point 0, comma t, and here you take 1, comma 1 minus t. Okay, suppose this is my space X, and now what you do, so you identify this point with this point. Okay, if I identify, so I'll get a quotient space. So the quotient space is called the Mobius band. So what you are doing here, you are taking so this, take a square and you twist and then glue. Okay, so if I do this thing, so I'll get a Mobius band. Okay, another way to get this Mobius band is the following. So these are my XYZ axis. Take this point 1, comma 0, comma 0, 0, and take the circle, unit circle in XY plane, passing through this point 1, comma 0, comma 0. And now you take a line parallel to Z axis passing through this 1, comma 0, comma 0, such that this 1, comma 0, comma 0, it is the midpoint of this line. And take this line to be open line segment. Okay. And now what you do, you rotate this line segment around z axis in the following way. Okay. So suppose you take this point and this angle is theta. Okay. And now what you do, you take this plane containing this z axis and this line, and suppose this is my plane P. So in this plane, now what you do, you rotate this blue line about this point by an angle theta by 2. Yeah. So this angle, it will be theta by 2. Okay. And now you vary theta from 0 to 2 pi. Uh, so this line segment, as it get rotated, so it will be twisted, and at uh, 2 pi, again it will come back to the original position. So after it will be, after getting a twist, it will come to the original position. So that will be your Mobius band. Okay. So now let me write down the surface patches for this Mobius band. So let us take this map. So let sigma d theta to be equal to 1 minus t sine theta by 2 multiplied by cos theta comma 1 minus t sine theta by 2 multiplied by sine theta comma t cos theta by 2. U is equal to t comma theta belonging to R2 such that minus half is less than t less than half, 0 is less than theta less than 2 pi, and u tilde is equal to t comma theta belonging to this R2 such that minus half is less than t less than half, uh, minus pi is less than 3 at theta less than pi. Okay, and so this Mobius band S is equal to sigma u union sigma u tilde. Okay, so this is my definition of Mobius band. And this Mobius band is not orientable. So S is not orientable. Okay. Suppose this is orientable. So we'll arrive at a contradiction. So suppose S is orientable. So then by that proposition, so then there exists a unit uh, there exists a differentiable unit normal vector field n from this S to R3. Okay. So now consider the meridian circle C is equal to sigma theta. So here I have taken sigma t theta. So it will be sigma 0 theta. So theta is varying from 0 to 2 pi. Okay, so this circle, it will be contained in the meridian of this Mobius band. Okay. So now either this n, it will be equal to n sigma, or it will be equal to minus n sigma. Okay. So n sigma, it is the surface, sorry, n sigma, it is the unit normal vector corresponding to the surface patch sigma u. So replacing n by minus n if necessary. So we assume n to be equal to n sigma. Okay. Let me try to draw a picture. So this is my Mobius band. And I have this meridian circle like this. And now what I am doing, so I am taking this normal at the point P. This P, it is varying in this meridian circle. Okay. So now what I'll do, so I'll uh, take this normal vector field on this meridian circle. Okay. Let us take, so the limit of n sigma, so sigma tends to, sorry, yeah. Before that, so let me do this computation. So sigma t vector product with sigma theta, so that you can show it to be equal to minus cos theta by 2 minus sin theta sin theta cos theta by 2 comma minus sin theta by 2. And so this vector product is a unit vector, and it is also normal to the surface. So this n sigma is equal to this thing, sigma t vector product with sigma theta. Okay, and we have assumed this n to be equal to n sigma. And now let us observe this thing. So limit theta tends to 0 plus n sigma. So let us take this limit. So this will be equal to, so from here, so from this equation, so from star, so what I'll get, so this will be equal to minus 1 comma 0 0. Okay, so this will be equal to n normal vector evaluated at the point sigma 0 0. Okay, and now if I take limit theta tends to 2 pi minus n sigma, so this will be equal to uh, again from the star, so what I'll get, this will be equal to 1 comma 0 comma 0, and again this point, this will be equal to n of sigma 0 to pi. Okay, so therefore, so this shows that n sigma 0 0 is not equal to n sigma 0 to pi. So this is a contradiction. As this 2 points sigma 0 0 and sigma 0 to pi are same. Okay, so this shows that S is not orientable. Okay, so I'll stop here.